Professor, do you think we'll ever be able to write down the fundamental laws?
I mean, we being humans, I think we have some understanding of the universe and the laws of nature, and we'll always make progress. But I don't believe that we'll ever get to what would be the fundamental laws, because I think there's always more than that we can understand as humans. And also, I think the laws that we have been able to get are always universal, but not always applicable. I mean, there's always exceptions to what we don't fully understand, and I think there's always situations where our laws will break down. So I believe more that what we will discover are things that are eventually understood from, assuming that there's something more fundamental, more microscopic going on, and that the laws that we are discovering are kind of more emergent from that underlying more fundamental description. And maybe we don't really need to know what this fundamental description is. We can still apply general reasoning to find these emergent laws. I mean, this is something that we have been very successful at in the history of science. I mean, we have discovered the laws of thermodynamics before even knowing that there were molecules or atoms. But eventually we were able to derive them from the assumption that there are atoms and molecules. So sometimes a law that we find gives us also a view of what might be underneath it. And I think many of our laws, and actually all of our laws, are eventually of that kind, in the sense that I think we will find those emergent laws that come from something more fundamental underneath, where as humans we may be not able to really write down the equations that describe everything. I mean, so I'm not a believer of that there will be a final theory where we indeed, when we write it down, there's nothing more to be discovered. I think as humans we'll always can continue and discover more, and there are always deeper questions that we have not been able to find. I mean, there's no final theory of nature.
But you do believe the final theory of nature exists? It just may be inaccessible to us as people?
I don't think that theory already is some assumption that we can sort of condense it into some finite set of equations. And I think our equations and everything that we have sort of developed as a language of describing nature is always a condensation of what is actually going on. I mean, I think the most maybe we should accept even that the universe is so complicated that it's just the most efficient way of doing everything that's in there, and that there's nothing there that we can write down that will predict all of the things that happen in the universe. And so I think there's a limitation there. I think it's not like we can assume that we as humans will be able to write down such equations. And even the concept of equation is kind of something that we thought about as humans, but maybe the language in which we have to write down, or in which nature is sort of written down, is not something that is an equation, or it's something that we can, as humans, can ever even get to.
Now, are you thinking about it in terms of an effective field theory, that there are high energy degrees of freedom that are irrelevant to us at some scale? Or is what you're saying about that there's something that's going to be more fundamental, quote unquote, microscopically, and it's just emergent levels that we have access to? Is that transcending even effective field theory? It's something that's independent of it.
So effective field theory is one of those other examples. I already mentioned thermodynamics as a very important example, where we sort of assume that there's some molecules and atoms that do certain things, and then Boltzmann was able to derive the laws of thermodynamics. Another example, and that's the one you're mentioning, is by Ken Wilson. I mean, I think his point of view on nature is very important. I mean, he realized that what we now sometimes call our most fundamental theories are actually field theories that should be thought about as effective field theories, where there's always some more fundamental, sort of more microscopic description. But what Wilson assumed is that the more fundamental theory is always going to smaller scales. He always said the fundamental theory is more microscopic and more underlying it. And he was assuming something about what we call scales, in the sense you have the small scales and need the heavy particles and things like this. And if you forget about them, you get at this effective field theory that you talked about. So effective field theory is indeed a very important concept in nature. But one of the things that we learned is that when we start adding gravity, the gravitational force, it somehow doesn't really fit very nicely in this whole effective field theory approach. In the sense that we would like to quantize gravity in a way where we don't need to assume that there's some, what we call usually cutoff, in the sense that we say there are some degrees of freedom that we don't take into account. So I think what we have learned in string, I'm also studying string theory, which is kind of a approach to quantum gravity. And there you see that there are situations where this reasoning of Wilson actually breaks down. So I think that Wilson was on the right track, but that we need a more general idea of that kind that will connect, what we call the more fundamental description to what we actually see today. Because, our theories will always be, as I said, in the current language at least, something that approximates what was a more fundamental description.
Your personal data is scattered across the internet like shrapnel. Incogni exists to retrieve it. When we explore consciousness or free will on this show, we engage in cataphatic inquiry, so positively asserting what something is. Data brokers do precisely that to you, asserting your address, your phone number, your social security number, even your relatives' information. These exposed data points are weaponizable. Data breaches increased by 211% from 2023 to 2024. Criminals use your information for identity theft, scams, stalking. You could spend hundreds of hours in a nation drained, exhausted, manually requesting removals from each site. Or Incogni can handle that for you automatically. They contact hundreds of data brokers on your behalf, repeatedly removing data. Their unlimited plan includes custom removals. So send any link where your data appears and they'll take it down. They're the only service independently verified by Deloitte. Just like we have to shed our braggadocious egos to make progress in philosophy and physics, and likewise, it's useful, even vital, to shed your digital traces. Take your personal data back with Incogni. Use code CURT at the link below and get 60% off an annual plan. That's incogni.com/CURT. They can't harm you if they can't find you. I'm curious about this word microscopic. So viewers who are listening or watching, they may have other views of what microscopic means. So one may be that you view it through a microscope. Another is that it's 10 to the minus 6 meters to 10 to the minus 9, somewhere between that range. But then another is just that you keep zooming in. And even this language that I'm saying, you keep zooming in to look closer and closer, implies that we're zooming in more spatially. Now, I've gone through your work extensively over the past few weeks and even months, and my understanding is that you've changed to even derive space itself from something else. So help me understand this word microscopic.
Well, microscopic means that it's also more fundamental, and there's some way in which we have to even change our language. Space and time is something that we have introduced as a reference frame in which we formulate the laws of physics. But if you think about the changes that have taken place within physics, when Newton wrote down space and time, he thought it was something absolute. When Einstein was thinking about it, he realized, space and time can be relative, and what you call time may be not the time of another observer. So we started thinking about space and time already in a different way. So what we are learning now is that there's something that even space-time should be made of. There's some way in which space and time can be constructed out of other underlying description. And so I think currently we are actually, even in my, I'm not the only one talking about this. In my field, we're really thinking about the microscopic description in a more abstract way, where space and time are not even assumed right from the beginning. There's some ways in which, for instance, we have microscopic theories that are living say, only very far away on some boundary of the space, and then somehow the space-time can be made to emerge from this more microscopic description. So what we call microscopic doesn't necessarily mean microscopic in our own space where we go smaller. It's more like it's a more fundamental description where the things that we write down really have a meaning in every scale, but also in the more, yeah, I mean, how to say it, underlying description. So mathematically, what it means, you write down first the equations that are for this microscopic theory, but I put it in quotation mark. It doesn't really mean that it's at
Right.
microscopic scales. But then you start deriving the properties that we see in our space and time from that, where space and time themselves are already not assumed from the beginning. So there's some way that space and time may emerge also from this microscopic language or description.
This entire line of thinking that there may not be fundamental laws that we have access to, in fact, even just saying fundamental laws itself is theory laden. Did that just start to occur to you later on in life? Because presumably, most people who enter physics, theoretical physics, do so because they heard about Einstein and they want to finish Einstein's dream of unification and finding the fundamental laws. So my question is about what motivated you to get into physics, and then how did your line of thinking as to what the fundamental laws are and our relationship to them and fundamentality and so forth change?
So I indeed started in physics, where the theory of everything, which is sort of what's even the name of your blog or your whole podcast.
Yeah.
I mean, it was kind of this fundamental idea, and it's true that Einstein is there on a pedestal, but Einstein is human. I mean, his theory is century old, and we have learned a lot more. And I have learned to be skeptical of other people's idea. I follow my own intuition. It's not like if someone tells me you should find the theory of everything, that the only thing I think about is that I should find the theory of everything. So I already started sort of, well, this is what's called intuition. I mean, you start feeling that cannot be the right answer. And that even has to do with sort of more of a philosophical idea. I mean, already you asked the question, can we ever find the final laws? I think as humans, we have limitations. So just the idea that we can find the final laws, I think, is hubris.
Interesting.
And if you really realize this is really a far-fetched idea that we as humans could ever be as clever to find the final theory, you start realizing it's the wrong track. It's the wrong question. But of course, you realize that Einstein and other very clever scientists, I mean, they found very fundamental equations that seem to apply almost everywhere. So how was this possible? And then you start realizing that as humans, we have been able to take what we observe and condense it in very small set of equations or experiences. That's what we do with our brain. We have so much information that gets in our brain that our brain is very good at condensing information and make it into very abstract notions. I usually use the example that if I draw this picture, people can recognize a house or something like that. Well, I've
Okay.
not drawn a house of that. I've just made some lines, and people can see, well, that looks like maybe the lines are representing what a kid draws as a house, but it isn't a house. It's an abstract notion of what a house is. And so we do the same thing in physics. We take something that we have observed and we give it a name and we give it an equation, a symbol in some equality and so on. But I think eventually nature is much more complicated than what we have done. We have really condensed everything in a much smaller parts. And this is why I think eventually what we write down will never be the full truth, but always a condensation of what's really going on. Sort of an abstract. So I think that in this idea of emergence, which is a much more general idea, is that there's always something more fundamental. So one of the analogies that I sometimes use is that there's this story about, well, people wondering why the earth didn't fall.
Right.
You know this? Well, people had in some ancient religion then the idea that there is maybe some giant turtle that is keeping the earth from falling because it has it on its back. And then they were happy because the turtle was keeping the earth from falling. And then people said, well, what about this turtle? Why doesn't it fall? And then the answer is, it's turtles all the way down. And so I think see every layer of the theory that we are making as one layer deeper, where we can make one step further, where there are some theoretical descriptions that we have found, like what we have now with the standard model and with general relativity. Is a beautiful description, but it's not complete. There must be a more fundamental one. But if you ask me, is that the final one? No, there will be another theory below that, another theory maybe below that. And so there's some way, I believe in this idea of what I call turtles all the way down, that we always will find the theories that are naturally emergent from the layer that's beneath it.
Okay, so there are a variety of questions I have. You said two interesting, more than two interesting, but two that stick out to me statements. So one was that you follow your nose. I want to know, were you always like that? Or did you have to train yourself to be like that? Okay, so let's bracket that because we can get back to that, but just a moment. And then number two, you said finding the fundamental laws may not be the right question, which then raises the question of what is the right question.
Now, that's a very good one. I mean, and I have to say that of course, when you enter physics, you have an ambition. You want to find new things that other people have not understood. That's one thing. One thing I have to tell you also, I mean, maybe you know this. I mean, I have a twin brother. You know, I have a twin brother who is also interested in theoretical physics. So this is certainly someone that influenced me a lot in my life, because even in high school we were already talking about what we were reading and what we were watching on television about. Well, we saw Stephen Hawking and also in the documentary about indeed particle physics, and the person that later became our advisor, that was Gerard het Hoofd, was also featuring there. So we were discussing about particles, about gravity, black holes, and Herman and I. So Herman is my twin brother. We already were discussing a lot during high school and during our studies. We even had some other fellow students. So we certainly had already done a lot in thinking about physics and these equations. And there's some way that even sort of the mathematical language that we also learned, I mean, everything that you sort of learn in university and also in high school is about also this abstract thinking. And there's some intuition that you get eventually about what you feel is the right direction. And I think that as a physicist, as a theoretical physicist, you should have this feeling about what is the right direction to go into. Well, I mean, I think every great physicist had this. I mean, if you read quotes by Einstein or I mean, he basically says it's not knowledge or even understanding. It's all imagination. That's the more important thing. That you have to be able to imagine things that other people have not been able to imagine. You have to go beyond the normal language that we use in every day. Because certainly when I write my equations, I have some image of what I'm writing down, but it's not always translatable to ordinary language. I mean, there's some way that we think in different terms than what we use in everyday life.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.